formulation of wave extremes, Poisson clumping heuristics. What is the main idea here? Let's assume that we have a realization of a Gaussian any random process between 0 and t, capital T. Eta t, generic random process. It can be anything. And let's fix a threshold h. Now I can compute what is the excursion time of eta t above h. I'm going to call this time tau of h, and of course now we know that tau of h is equal to what? Is equal to the probability that eta is equal to z times dz, integral between h and infinity, and then I multiply by t. This is simply the probability that eta is greater than h times t. And of course I assume that I know the generic random process that is stationary. So we know what is the PDF of eta, which is stationary. And I can interpret this probability as the fraction of time during which eta is greater than h. And this is also equal to this integral. Of course, the same excursion time is also equal to what? If I look at the excursion time, I see that is given by this time segments is right. So which I can call T1, T2, T3, and so on. And this, of course, when the threshold h is very large, for h much larger than sigma, these excursion times are simply equal to the time duration of a peak greater than h. Okay, let's call this. Let's assume that this amplitude is equal to z. Okay, and instead here we have the variable h. So this quantity here is z minus h, which is greater or equal than 0. And of course, this time t will be dependent on z and h. Let's call it zh. Okay, so this is basically the, let's call it the footprint of a crest. Okay, and let's assume that we have this information. I can compute this exclusion time in an alternative way by summing up all these footprints for all the crests that occur between 0 and t. Okay? So what does it mean? It means that I can the excursion time above h, which is equal to the interval between h and infinity of the probability that eta is equal to z dz. This excursion time is also equal, tau of h is also equal to the sum over j of all the footprints tau h zj of crests with amplitude in zj and zj plus dz. Okay? Because that's what it is. So what does it mean? It means now let's call with exc of z dz average number of crest with amplitude in z plus dz per unit time. Okay? Then what I do, I multiply by t. So all of this is what? Average number of crests in 0t with amplitude in z and z plus dz. But then, now I know the number of, now what I know basically. I know this is the level h. Here I have my random process between 0 and t. So now I consider all these footprints. This is tau zh. If I multiply by tau zh, which I need to define it, but we will be able to formulate a generic expression for generic random processes. Now I have a number of crests in 0t times this footprint, which is as a unit of time. And if I take all this expression and I integrate between h and infinity in the z, I'm gonna get the excursion time above h. Okay? And so we have what? We have that we have this expression, which we compute by simply knowing the probability structure of how random process, generic, until now we have just a generic stationary random process. But now we also have this other expression, which is written in terms of extremes. This is basically excursion time, the excursion times in terms of extremes. And of course, this is true only when h over sigma is very, very, very large. Okay? So, under these conditions, we can say that this has to be equal to this. Okay? And so, what does it mean? That we get this, we have that integral between h and infinity of ex cz dz, actually, sorry, tau zh. Actually, you know what, let me do it correctly. So we have that the integral between h and infinity of exc z tau zh times t, I can bring t outside, in delta z, has to be equal to the integral between h and infinity of the probability of eta equal eta z dz. What we got here is a Volterra integral equation of second kind. Integral equation of second kind for ex of z, which depend only on the structure of the extreme. This quantity here, it depends on the wave extreme structure. Let's call it shape. And we also need the probability density function. Of eta. So, of course, these are quantity that can be easily estimated from data empirically. Then you plug it here, you solve numerically your integral equation, and then you get an expression for, you have an approximation of the expected number of crest above h, okay? Or for special cases, if we can characterize for a special shape of wave extremes, this integral equation can be solved. And for example, you can consider for example, a triangular shape, or you can have a cusp shape, or you can have a parabolic shape. For example, this is when eta is going to be proportional to t power of alpha. The triangular shape is for alpha equal 1. The parabolic shape is for alpha greater than 1, and the cusp shape is alpha less than 1. Okay? So here we have cusp, here we have triangular, and here we have type parabolic, okay? Parabolic. So for this kind of wave extreme shapes, this integral equation can be solved analytically. So you can find the generic solution on my GPO paper 2010. So Google it, and you will find basically a generic solution for this integral equation for a generic probability density function. Okay. Of course, these two are related. Okay. Now, what I'm going to do, I'm going to show you how to solve this equation for Gaussian processes, because we can get a very nice expression for this footprint of a large crest. Okay, indeed. So we have what? We have that the integral